It was 1971 in Santa Clara, California. A team of engineers at Intel, led by Federico Fagin, was racing against time. Their mission? To shrink an entire computer's brain onto a single chip. The result? The Intel 4004, the world's first commercially available microprocessor. With just 2,300 transistors, this tiny chip could perform 60,000 operations per second. It was a revolution in miniature, paving the way for everything from calculators to spaceships. The age of silicon had begun. The Busicom 141 power factors calculator wasn't just another adding machine. It became the first device to use the Intel 4004, proving microprocessors could replace entire circuit boards. Japanese engineers had originally designed a complex 12-chip system, but Intel's Ted Horf saw a better way. By convincing Busicom to use their single-chip solution, Horf unknowingly created the blueprint for modern computing. Within months, the 4004 was being used in traffic lights, medical equipment, and even NASA prototypes. Just 2 years later in 1973, Intel doubled down with the 8008. This 8-bit processor could handle twice as much data as its predecessor, enabling the first primitive personal computers. The Cell-by-8H hobbyist kit and the Mark 8 appeared, built by enthusiasts in garages across America. Though primitive by today's standards, these machines proved microprocessors weren't just for corporations, they could empower individuals too. The seeds of the PC revolution were planted. 1978 marked a turning point. Intel's 8086 processor introduced the x86 architecture that would dominate computing for decades. With 29,000 transistors and a 16-bit design, it powered IBM's first PCs. But the real genius was backward compatibility, a principle Intel maintained for generations. Meanwhile, over at Motorola, the 68000 series was winning over Apple and early workstation makers. The stage was set for an epic architectural battle that would last 30 years. By the early 1980s, microprocessors were escaping corporate data centers and entering homes. The IBM PCs for 0.77 MHz Intel 8088 chip made computing accessible, while clones from Compaq and others drove prices down. Across town, Apple's Motorola-powered Macintosh introduced the graphical user interface. Meanwhile, hidden in labs, RISC architecture promised a more efficient future. The personal computer era had arrived, and with it, the first generation of computer enthusiasts and programmers. The late 1980s saw processor speed skyrocket. Intel's 80386 brought 32-bit computing to the masses, while Motorola's 68030 powered advanced workstations. Clock speeds broke the 20 MHz barrier, and software grew more demanding. But with great power came great heat. Engineers faced new challenges in cooling and power efficiency. The stage was set for the processor wars of the 1990s, where megahertz numbers would become marketing gold and the PC would cement its place in every office and home. 1993 marked the birth of an icon. Intel's Pentium processor wasn't just another chip, it was a brand, complete with its own jingle. The P5 architecture delivered 60 MHz speeds and superscalar design, executing multiple instructions simultaneously. But fame came with scrutiny. The infamous FDIV bug forced a costly recall. Meanwhile, AMD and Cyrix began challenging Intel's dominance with cheaper alternatives. The processor had become the PC celebrity component, and consumers were starting to pay attention to specs. The late 1990s became a battleground of clock speeds. Intel's Pentium 3 hit 1 GHz in 2000, while AMD's Athlon often outperformed Intel at lower speeds. Consumers obsessed over benchmarks, and PC magazines published monthly speed comparisons. But this race came at a cost. Power consumption soared, and cooling solutions grew louder. Engineers realized raw clock speed couldn't scale forever, setting the stage for the next revolution: multi-core processors that could do more without running hotter. 2005 changed everything. With single-core processors hitting thermal limits, Intel and AMD both released dual-core CPUs. The Pentium D and Athlon 64X2 could run 2 threads simultaneously, offering better performance without higher clock speeds. Software had to adapt, but the future was clear: parallel processing was the only way forward. Within years, quad-core processors became mainstream, and programmers faced the challenge of writing multi-threaded code. The era of brute force speed gave way to sophisticated architectural improvements. As smartphones emerged, a different kind of processor rose to prominence. ARM's energy-efficient designs, originally developed for Acorn computers in the 1980s, became the backbone of mobile computing. Unlike Intel's power-hungry x86 chips, ARM processors sip energy, enabling all-day battery life. Apple's A-series chips for iPhone demonstrated how mobile processors could rival desktop performance. The computing world was splitting into two camps: x86 for traditional PCs, and ARM for mobile, a divide that would eventually blur. In 2020, Apple shocked the industry by announcing its transition from Intel processors to its own ARM-based silicon. The M1 chip delivered unprecedented performance per watt, running cool and efficient in sleek MacBooks. This move validated ARM's potential beyond mobile devices and signaled a seismic shift in computing. Microsoft and Qualcomm responded with Windows on ARM, while Intel scrambled to improve efficiency. After decades of x86 dominance, the processor world was becoming pluralistic again. While CPUs evolved, another processor was quietly transforming. Originally designed for rendering graphics, GPUs proved exceptionally good at parallel computations. NVIDIA's CUDA platform turned GPUs into general-purpose processors, accelerating scientific research and, eventually, AI training. The company's Tesla architecture became the backbone of modern machine learning. Suddenly, gaming cards were powering breakthroughs in medicine, astronomy, and autonomous vehicles. The processor landscape had expanded beyond anyone's predictions. Today's cutting edge isn't general-purpose CPUs or even GPUs, but processors designed specifically for AI. Google's TPUs, Apple's Neural Engine, and NVIDIA's Tensor Cores accelerate machine learning tasks with unprecedented efficiency. These chips can perform thousands of matrix operations simultaneously, mimicking neural networks. As AI becomes ubiquitous, from voice assistants to self-driving cars, these specialized processors represent the next evolutionary step: hardware designed not for general computing, but for thinking. As we look ahead, processors face new challenges and opportunities. Quantum computing promises exponential speed-ups for certain problems, while photonic chips could transmit data at light speed. Neuromorphic processors mimic the human brain's architecture. Yet the humble microprocessor, now over 50 years old, remains at the heart of our digital world. From the 4004's 2,300 transistors to today's billion-transistor AI chips, the journey of silicon continues to reshape human civilization in ways its inventors could scarcely imagine.